Hi, it's time for another math easy solution. To discuss further into conic sections and polar coordinates. And this video will cover rotation, also example 5, and some brief notes on eccentricity for polar equations of conic sections. But first I want to make a note, MES note. So I was planning on making separate videos on rotation in example 5 for my conic sections in polar coordinates section or video series. Yeah, but my dive in the fascinating world of hashtag suppress science has forced me to change up the way I make my math videos. Yeah, basically if you've been following along my other videos, I'm not a big fan of the quote laws of physics and whatnot. So we'll see where I come up with later, so just follow along. There's be some pretty exciting stuff I got planned. So thus I plan on making longer individual math videos that encompass more thorough a topic and its accompanying examples. This way I can save time in the video production process by uploading less videos, but nonetheless cover more material than I would do so otherwise. Anyways, I got big plans, so hashtag stay tuned. And so I'll do videos in more like this format where I'll have topics to cover and cover a bunch at once. So even though the video might be long, it'll still cover a lot of material. And we'll probably even go through my calculus book much faster and get to other books. So anyway, so let's go over the topics to cover in this video. So polar coordinates, rotation. Then I'm going to go an example on rotating a cardioid or a heart shape. A polar function, as I covered in my earlier video, and also just a general, just go over general polar rotation and conics in polar coordinates, example 5, and then effects of varying eccentricity. So let's just jump right in. So polar coordinates, rotation. To illustrate how functions in polar coordinates are rotating, consider the following example. This example states, how are the graphs of r equals 1 plus sine theta minus pi over 6 and r equals 1 plus sine theta minus pi over 3 related to the graph of r equals 1 plus sine theta? Alright, so let's just jump to the solution. So first off, recall that from my earlier video that the polar equation r equals 1 plus sine theta, this basic one right here, without these terms there. Yeah, this forms a quote cardioid or heart shape, as I covered in my earlier video. Put a link in the description below. And here it is. If you graph it, looks something like this. Just an upside down heart. R equals 1 plus sine theta using the Desmos graphing calculator. So now let's compare this function with the functions r equals 1 plus sine theta minus pi over 6 and r equals 1 plus sine theta minus pi over 3. Just want to double check. Yeah, so there's the exact ones we're trying to graph. So first off, what we'll note is at theta equals to 0 for the basic one, we have r equals to 1 plus sine theta or sine 0. So that's this one right here, and this equals to, r equals, this one's going to go to 0. So this equals 1 plus 0. Remember, sine 0 is just is a 0. This equals to 1. Yeah, so in other words, what we have is at the angle, remember the polar coordinates is the pole, so the angle, the flat line on the positive x-axis, that's going to be at theta equals to 0, like that. So then this point is going to be, this distance is going to be 1, or r, so the coordinate at this point is going to be 1 and 0, like that, where this is basically our r and theta, like that. Alright, so that is for this function over here, but for the other one, if we were looking at this one here, we want to get the same result of 1, and basically what we could do is, if we just look at this, just plug in pi over 6, so they cancel, it becomes 0. So at theta equals to pi over 6, what we have is r equals to 1 plus sine pi over 6 minus pi over 6, like that. This is going to equal, again, 1 plus sine 0, and this is going to be, 0. It's going to be 1, like that. So the exact same thing. And this could be represented as, this one's going to be rotating, in fact. So it's going to be rotating by pi over 6, like that. So then we're going to get a point over there, and this point's going to be something like here. This is going to be 1 pi over 6, something like that. And let's go further. Now at this one here, the same thing, we could plug in now pi over 3. So at theta equals to pi over 3, we have r equals to 1 plus sine pi over 3 minus pi over 3. These cancel 1 plus sine 0. Sine 0 is just 0. This equals to 1, like that. So again, this would be shifted across somewhere around here, and this is going to be 1 and pi over 3. So something like that. This is going to be at pi over 3 angle. Now to give further illustration, let's look up at this angle or this point right here. Remember, this angle is, and I'll just draw an arrow like that. This angle is pi over 2 or 90 degrees, and or tau over 4 if you've seen my earlier videos on why pi is wrong. But anyways, I digress. So this is going to be at this coordinate on this graph is going to be 2 and pi over 2. So r is 2, distance from the origin, and I'll show you it is in fact that, and then the angle is pi over 2, like that. So just to illustrate this further, also, and right here at theta equals to pi over 2, for the basic one, r equals 1 plus sine theta. Recall that sine pi over 2 is just, well, 1. So recall from my earlier video, that's just equals to 1. So we have 1 plus 1 equals to 2, like that. And then likewise at the other one, at this over here, what we're going to do is take this pi over 2, and then we're going to shift this even further. And what I'm going to do is I'm going to shift this about this curve like that. I mean, this is going to be pi over 6, and this is for the other one. And I'll show you here it's going to be the same thing over there, the same too. So at pi over 2 plus pi over 6, we're adding an extra angle, and I'm going to throw it inside this function. This is going to be pi over 2 plus pi over 6. So we get r equals to 1 plus sine of pi over 2 plus pi over 6 minus pi over 6. These cancel. This just equals to 1 plus sine pi over 2, like that, which is just this part. That's just 1 equals to 2. So there we have it. And in fact, when we scroll over here, so this point is going to be, well, at this somewhere over there, it's going to be at 2 and pi over 2 plus pi over 6. So we can add those up or just leave it like that, just to illustrate it. And likewise, we could rotate, instead of that, we could rotate it by, well, pi over 3, like this. Pi over 3, like that. This is going to be somewhere around here, so it's again, as you can see the rotation, this is going to be at 2 and pi over 2 plus pi over 3. Because remember, pi over 3 is a bigger angle than pi over 6. You're dividing by a smaller number. So let's go further, and here at, and I already drew what we should get, and that is what we will get over here. So plug in pi over 2 plus pi over 3 into that one, so we get pi over 2 plus pi over 3. We get r equals to 1 plus sine pi over 2 plus pi over 3, and then subtracted by that pi over 3. Those cancel. We're just left with 1 plus sine pi over 2. These cancel. Then that just is 1 plus 1 is equal to 2. Yeah, so thus what we end up having is, so thus we have, if we're moving from this this formula, r equals to 1 plus sine theta, like this. So we're gonna, let's say we're shifting over from this one, compare these all, r equals 1 plus sine pi over 3 minus, the other way around, theta minus pi over 6, and then the last one onto this side, r equals to 1 plus sine of theta minus pi over 3, like that. So if we're comparing these three formulas, what we notice is, well, for this one, when we have the coordinate 1 and 0, scroll up here, so that is over here, 1, 0, it becomes over here 1 pi over 6, and it goes to 1 pi over 3. And that is, well, when we have 1, 0, 1, pi over 6, pi over 3 over there. And likewise, this one is pi over 2, 2 and pi over 2, and then we just add pi over 6 and pi over 3. So in other words, we go from here, we're rotating, we get 1 and pi over 6. And likewise over here, on this side we get 1 and pi over 3. And likewise for the 2 and pi over 2, so 90 degrees, or tau over 4. So we get over here, this is going to be 2 and pi over 2 plus pi over 6. So we're just adding another 1, we get to 2. So you could think of it as any point, we just add that pi over 6, and then it's going to be the exact same coordinate there. Here's going to be now 2 and pi over 2 plus pi over 3. So we're always rotating to the counterclockwise. This is counterclockwise. Yeah, so I wrote that down. So in other words, the cardioid function or the heart-shaped function r equals 1 plus sine theta gets rotated counterclockwise by pi over 6 and pi over 3 respectively. And if we graph that out using the decimal graphing calculator, so here is in black like this, and there's the 1 0, and notice how it's just getting rotated. Now we have the in red r equals 1 plus sine theta minus pi over 6. So can you see the, yeah, you can notice the rotation. Then this one over here is getting rotated further out like that. So very, very fascinating stuff here. Yeah, and in blue is the 1 plus sine theta minus pi over 3, and that one's the rotated the most out there. So let's draw something like this over there, and then this one, as you can see, it's rotated way out over here. Fascinating stuff. And also when you look at the pi over 2 part over here, it goes somewhere like this. Where would this go? It would go somewhere like this, and somewhere over there, I assume. Yeah, just fix up those arrows. Something like that. I'm not 100% sure, but yeah, you get the idea. Yeah, and now we're asked to look at it in more general terms. So in general, how is the graph of r equals f of theta minus alpha related to the graph of r equals f of theta? And here I quickly added just another header just to match up with the topics to cover it as in the beginning of the video. So polar rotations in general. So now let's look at this to just see how is this related to this graph in general when we have this minus alpha as the minus pi over 6 or minus pi over 3 in the above example. So let's look at what we have here. I'm going to let's draw this more over here. If this is going to be our polar axis here, P, and let's say we have a weird function looks like this. So yeah, just something like this. Actually, I just made it a bit smaller. So let's say this is our r equals to f of theta, like that. And let's say we have just a random point over here, and this is going to be at an angle like this. This angle is going to be, well, theta with a 0 like that. We'll call that theta naught, and then here is going to be the distance r naught. So the coordinates here is going to be r naught and theta naught on this point. And this is on this function r equals f of theta. So in other words, this one you could also write this as of like this. The r is going to be f of theta naught, and then theta naught like that, just for completeness sake. Yes, so now what I'll write down is, well, for any point r naught and theta naught, like that, this point for example, on the function r equals to f of theta on, not or, on f of theta. And so for every point on that, the point, now if we were to rotate this, so the point r, this one r naught, then we're going to add this up, so theta plus alpha. So if we're shifting it by this plus alpha like that, then this is, I'll show you how it relates to this theta minus alpha graph. So if we're adding this here, then this point is on r equals to f of theta this one right here, theta minus alpha, and this right here is because capital letters, because it's want to make it clear, and this is because r naught. Yeah, so R naught is equal to, well, f of this part right here, f of theta naught. So when you plug in that theta inside, and this also is equal to, yeah, this is also equal to, well, this function here when we plug in this instead. So this equals to f of theta naught. Yeah, so I'll put a square bracket. So this is equal to, when we plug in this one, theta naught plus alpha, and this is, well, for this function, this is minus alpha, like that. So then these would just cancel, and we're just left with, well, this just equals to f of, well, these cancel, f of theta naught. Yeah, so in other words, basically we're going to get the exact same point here. So this is r, like that. If we're going to be rotating this by, I'll rotate this somewhere like this, and this point, I'll rotate this, I'll call this alpha, like that. So if we're rotating that all the way across, this is going to be the exact same point, but on this side over here. I'll just draw this here. This point is going to be, well, r naught, or r0, r naught, and then theta naught plus alpha. So it's a combination of the two angles. And then if we were to graph this out, it's going to be, well, shifted. It's going to look something, I'll just draw this better. Let's see if I have my artistic drawings. It's going to look something like it's going to look something like this, or something. Okay. Yeah, alright, so I quickly just drew something like this, something artistic. This is basically this shape just rotated across over here, and I'll write this addition. This is going to be alpha, or theta naught plus alpha. And now this new function is just r equals to f of theta minus alpha, like that. And as you can see, when it's like this, and when we add theta plus alpha, they just becomes the exact r value, like this. So we're always going to get the exact r value. Doesn't matter if you go from here, you'll get to somewhere over here. For example, this will get to this exact same point, same r values, but just rotated by alpha, or whatever angle you're rotating by. Yeah, so thus, in general, the function r equals f of theta minus alpha is the same shape as that of, I don't know why this is bolden, of r equals f of theta, but shifted, or in fact, I'll just write rotated counterclockwise, yeah, by alpha about the origin, like that. So yes, everything is rotating about the origin, like that. Fascinating stuff, or the pole, or whatever you want to call it. So now let's go to another section, or another part of the topics to cover, and that's conic sections, polar coordinates. And now we could apply the same method as above to rotate conic sections in polar equations, which is in fact much easier than in Cartesian equations, and as shown in the following example. And I'll rotate a conic section as opposed to the cardioid. So let's look at this example. It says if the ellipse of example 2, so recall in my earlier video on example 2, is rotated through an angle pi/4 about the origin, find a polar equation and graph the resulting ellipse. Alright, so let's look at the solution, but first off, let's recall from my earlier video on example 2, and I'll put the link in the description below. Basically, we have this right here. Looks like here r equals 10 over 3 minus 2 cosine theta. The directrix is just that vertical line, x equals to -5, like that. Yeah, so here note the directrix at x equals -5, and the focus at the origin, so we have one over there, is one of the focus of the ellipse. And so we want to rotate this by pi/4 about the origin, assuming it's counterclockwise. So if we were to rotate the ellipse, assuming in the counterclockwise direction, then we should just replace theta by theta minus pi/4, as explained above. So thus the new equation is, so we have over here r equals to, well, 10, and then this is going to be 1 minus, 3 minus, not 1. So 3 minus 2 cosine, and now theta minus pi/4, like that. So there is our new equation, rotated by pi/4. And in fact, doesn't get much easier than that in polar equations. Just replace it and you're done. As opposed to Cartesian, you can do a bunch of other algebra and other stuff like that. So now if we graph it, we get the following. So if we graph the two equations. As you can see, it's rotated across. Yeah, it's rotated by pi over 4, which is, in fact, that's going to be, well, pi over 2 divided by 2, or in other words, 90 degrees divided by 2, that's 45 degrees. And you can, in fact, see that because this is just a perfect square right here. This is going to be 1, 1, 1. So this cuts straight through the middle here. This cuts straight through the middle, and that is the highest point. That's this point right here. That's at 10, 0. This is going to be now 10 pi over 4, like that. So yes, this is rotated about the origin at pi over 4 radians, or this is 45 degrees, or pi or tau over 8. Yeah, in tau, whatever units. Again, if you watch my earlier video on why pi is wrong. But yes, I digress. So notice that the ellipse has been rotated about its left focus, which is in fact the origin. So the focus stays the same. It's just going to be rotated all the way across. Alright, so yes, fascinating stuff indeed. And now let's jump to the last topic of this video, and that's the effects of varying the eccentricity. So recall first of all that the polar equation of a conic section, which I derived in my earlier videos, over here a polar equation of the form r equals ed, where d is the direct distance to the directrix, e is the eccentricity. So divided by 1 plus or minus e cosine theta, or r equals ed divided by 1 plus or minus e sine theta. The cos and sines depend if it's vertical, I mean horizontal or vertical. The plus or minus depends if it's opening up to the left or to the right. And you can watch my earlier videos to see more on those. But basically, these equation or equation of any of this form represents a conic section with eccentricity e and the focus at the origin. And the conic is an ellipse if e is less than 1, a parabola if e equals to 1, or a hyperbola if e is greater than 1. So now let's graph a standard conic with d equals 1 and a plus in the denominator. So we'll look at this, and actually a cosine. Yeah, here I just wrote that a bit better. So, and with a 1 plus e cosine in the denominator. So we'll just look at this side over here, but positive on this side, like that. And with varying values for the eccentricity e. So we're going to vary this. So here's what I've done. I've graphed this out in a Desmos graphing calculator, but I just want to make a note right here. Yes, a note, I used the variable a instead of e because e is already predefined as the exponential number e equals 2.718281883, etc. It keeps going on and on. So if we look at this graph right here, so this is r equals, yes, I let over here, you had d equals to 1. Yeah, as noted over there. So the d equals to 1, so just a, r equals a times 1 divided by 1 plus a cosine theta, or just a over 1 plus a cosine theta. And I just varied the values here. Here's at 0.1, we get, it's almost like a circle. It's not exactly as you see, it's a bit off center. And the origin is the focus. Remember that. This is the focus, so it should be completely centered for a circle. So let's just graph this out, or just click this here to see the graph. Alright, so here I am on the Desmos graphing calculator. I'll just move this around to the left. Let's just see what we can come up with. So now what we could do here, we could vary this by pressing plus, and as you can see, it gets bigger and becomes more elongated. It gets really big and then becomes a hyperbola. So fascinating. So I have this going up to 4, and it goes back down. So it becomes flatter and flatter as the numbers get bigger and bigger for the hyperbola. And then watch it get stretched back down. So we're going back down. I'll make this even. So I'll make this slower once it gets closer to 1. Let's just slow this down. So when it becomes 1, let's see what happens. Let's speed this up. And then slow it down. Oh, whoops, let's just go back to 1. Yeah, so when it gets to 1, it's a parabola. There's only one side like that. Fascinating. And this is press plus. And is it reset like that? Actually, yeah. I'll go back to the 1 over here. Press play. Let's go here. Press play, so it goes backwards. Interesting. Alright, so I just paused it and just got over here. So notice it's a hyperbola. Press play as it gets smaller and smaller. This just vanishes when it gets to the 1 value. So yeah, this is going, it's just running away. Fascinating. And then it becomes a ellipse after it changes from 1. It's fascinating stuff like that. And then it gets smaller and smaller. As A is getting smaller, this whole thing is getting smaller and smaller. Oh, whoops, where am I? There I am. So yeah, it's getting smaller and smaller as it's trying to be a circle and going back up. It got bigger. So yes, fascinating stuff indeed. Here I took a bunch of screenshots. So here's at 0.1, looks almost like a circle. Here's at 0.5, it becomes more like an ellipse. And then at 0.68, it's becoming elongated. And also larger. 0.86 is getting even stretched out. 0.96 is getting super stretched out, and then exactly at 1 there is a just a parabola, and then anything greater becomes a hyperbola. As it's getting bigger numbers, it's getting more and more flatlined like that. Fascinating stuff indeed. So notice that when E is close to 0, the ellipse is nearly circular, whereas it becomes more elongated as it approaches 1 from the left side. And when E equals 1, of course, the conic is a parabola. That was exactly when E equals to 1 over here. Aside from when it's 1 and becomes, well, ellipse or a hyperbola. And when E is greater than 1, the conic is a hyperbola and keeps extending as it gets larger. And here's wrote that down as well, as E gets larger, like that. So also notice that as E approaches 0, the ellipse gets smaller and smaller, i.e. approaches 0 as well. So it's all getting to exact spot 0, becomes like a circle, but it's very, 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 very small. Very fascinating stuff indeed. So it's interesting stuff indeed. Look at the scale here, 0.2, 0.2, and this at 0.01 I made it. It gets smaller and smaller. So absolutely fascinating stuff. Anyways, that is all for today. Hopefully you learned from this pretty extensive video. Covered a lot of topics. In later math videos that I'll do, I'll probably just cover an entire chapter or part of a chapter, but I'll try to do a lot of them at once so I can have enough time to go over my hidden science, suppressed science, free energy, anti-gravity video series, which I have big plans in the works. Anyways, all for today. If you followed along and there's topics to cover, I'll be including these more in later videos so you can see exactly what I'll be covering it, and and yeah, follow along. Hopefully it will help a lot, as I'll eventually be covering a bunch of math and science textbooks, all in a short amount of time. Anyways, all for today. Thanks for watching, and like always, you can download these exact notes in a link in the description below, as well as viewing me. I'm viewing these notes in article format on Steemit, and also make sure to check out my my math chat rooms, as well as my Reddit and Vote math forums, and post any cool math or science related stuff you want you have. Anyways, all for today. Thanks for watching, and stay tuned for another math